Hello, so this is the fourth lecture from the series on noncommutative geometry. So what we'll do today will be to finish somehow what we started last time. So last time we've seen that we can axiomatize these noncommutative geometries. I mean, not the analogues of Rn, Cn themselves, which don't exist, these free analogues, but rather the objects one level below, meaning a sphere, torus, quantum group, and reflection group. And so I had the axioms coming from correspondences, the 12 correspondences between these objects. And as main examples, we had, of course, the geometry of Rn, the geometry of Cn, the geometry of free Rn, and of free Cn. So now with these axioms that we found the last time, we'll explore a bit what else can be constructed. So we'll look for intermediate things between classical and free, and also between real and complex. So the result somehow will be that for both intermediate questions, there is a kind of standard solution. So we'll end up with 9 geometries, and then will come some classification results stating that under some suitable axioms, these 9 geometries are the only ones. So that is the plan for today. Now let's find this presentation. Here we are. So basic non-commutative geometries. So these are, we already have 4 basic ones, right? But now we want to get bigger. We have 9 basic things. So as I was telling you, no free Rn, no free Cn, everything comes from this. That's why we have to introduce all this mess with the S2K, right? Because there's no free Rn, no free Cn, at least in some reasonable sense. I mean, operator algebra sense. Things just are not bounded. You cannot construct analogues of this. So that's why we axiomatize such things. And we have 4 main examples. And from now on, we can use the symbols Rn plus, Cn plus. These things don't exist, but the quadruplets exist. So these things exist as non-commutative geometries. We'll just denote it like this with a plus. What are the axioms? Let's recall also this. So we take quadruplets between classical real, which is the smallest somehow, and free complex, which is the biggest. And then we need 12 correspondences between these things. And actually, things finally reduce to 7 correspondences. You see, I have 7 equality signs over here. And this, let's remind quickly what these are about. So S should be the first column space of the unitary group. It's like a homogeneous spacing. Then these intersection things, which are trivial. Then U must be the quantum isometry group of the sphere, which is kind of easy in practice to verify too. You have this Bhumiko-Swami tricks that you have to apply. Then U must appear from the torus by taking the joint generation of the N. This is very tricky, so it uses all this curiosity stuff, which is recent and very technical. Now what else do we have? This is an intersection. Everything, intersections are something trivial always. But then we have this too. I mean, K must be the reflection group of the torus. This is tricky too because G plus of T alone involves twisting general. It's quite complicated in the free case. So I have a difficulty here with the generation, another difficulty here. And actually, quite surprisingly, there's a difficulty in the beginning too, with S being equal to issue, the first column space. We need to know Weingarten formula and these things for proving that. So there are 3 difficulties. Now, as the plan for today, so I have these 4 examples at the corners, Rn, Rn plus, Cn, Cn plus. So look for intermediate things between classical and free, and there will be something that we denote with a star called half classical geometry. Of course, both in the real and the complex case. And then we'll look for hybrid things between real and complex. And here also there's a standard choice. You multiply the real thing by a copy of T. So that's how we'll end on the 9 diagram. Technically speaking, yeah, we'll have to check these axioms. So I was talking about, so it's going to be a Weingarten, what was it? Let's go back. So Weingarten here, liberation questions here, twists here. So we'll go a bit fast, there won't be proofs. So I will just tell you the results. And then we'll get into classification results. So I'd like somehow to to have a result stating that under strong axioms there are no other geometries. And here, once again, we'll get into a very advanced classification business. I mean, state of the art. All this is-equal group work of Weber with Raum and Tarago and Mang. So this will be used, plus some extra tricks like orientation slicing. And so yeah, we're getting here into research. So this will be, as usual, a 30-35 minutes presentation, but mostly statements, right? And finally, on top of that, we'll discuss also bit extensions, because these things, for instance, they can be twist, for instance, that's for sure. And twist at -1, so we'll discuss how this twist could fit into a large framework. So a lot of things to be done, and don't worry if there are no proofs, but well, that's it. We're into research now. In the first parts of the course, lecture 1 to 3 are elementary, now 4, 5, 6 are advanced. 5, 6 will be about developing these geometries. I mean, finding manifolds, homogeneous spaces, also integrating over them. So let's get started. So first, we'll look for something intermediate between classical and free. So is there something standard there? And the simplest idea, there are many ways of looking at this. A simple idea is just looking at spheres. So let's try to consider the sphere Sk, obtaining the following relations. A1 up to Ak equals to Ak up to A1, written in the other sense between coordinates. So see what we get, right? This is intermediate between classical and free. And actually, there are only 3 cases if you do a bit of algebra. I mean, you just have to play with sum of xi squared is 1, right? It's very easy. And things collapse to only three things. So you get either when you put no relations, I mean, k is 1, you get the free sphere. When k is even, you always get the real sphere. You have to play a bit with this quadratic relation. It collapses to a b is ba. And when k is odd, they are also all equal. So let's say they're equal to S3, the first one. So this is interesting because we have classical free plus a new thing. So that's the new thing probably we're interested in. So S3 is the sphere generated by A1, A2, A3 is A3, A2, A1. So ABC, CBA if you want, formulated in a nicer way. So let's call it Sn minus 1 R star. So why star? This comes also from easiness, because ABC, CBA, this corresponds somehow to this diagram. This, and this is like a big star. So the star is therefore reminding us this diagram. We'll get later into easiness. So that's natural candidates. Now, well, of course, you can do the same thing for orthogonal group, octahedral group. Just add ABC to the coordinates. I mean, take the free versions of everything and add ABC, CBA to the coordinates. We can also do it in the complex case. Once again, take the free complex things and add ABC, CBA to the coordinates and their adjoints. So what I have to do now is there are 3 things. So first, we need some tools for studying these objects, right? Remember that the NCG axioms are quite technical. You can do that if you don't have a knowledge of the things. So we need tools. With tools, we'll check the NCG axioms. And then we'll also establish some further uniqueness results, because the thing which was on the previous slide, this one, is a bit ad hoc. I mean, you see, these are like mirroring commutation relations, but you can come with many other things. So yeah, we'll do that too. So tools, how to study this? So this is basically due to Julien Bichon and Dubois-Violette also. So the idea is the following. Let's look at the sphere first. The other ones will be the same groups and all that. So if you look at the sphere ABC CBA, implies that the projective coordinate commutes. I mean, the projective coordinates are the ABs and the CDs. I remind you that they are in the real case, everything is self-adjoint. And these commutes, I mean, ABCD is CDAB. You get it right away from ABC CDA. So this means that the projective space is classical of the sphere. Now, so it's included, if you want, in the complex projective space. Now I can prove it also in the other sense. For doing it in the other sense, you need a model for this, this half classical guys. And there is a very simple model. So the coordinates, you model by them by anti-diagonal matrices like this. Zi are the coordinates of the usual complex sphere. So you see these matrices are self-adjoint and they have commute. I mean, the anti-diagonal things is very easy to see that they have commute, right? Because you compose two of them, you get diagonal, and the third one anti-diagonal. And no matter how you compose them, you get the same anti-diagonal thing at the end. So I have this model, and so this means somehow that your thing is big enough, so it's equal. The projective space of the half classical real sphere equals the complex classical projective space. That's one thing. Now, getting to the spheres, well, the idea is that the sphere just appears as an affine lift of this projective space. But affine lift inside the real sphere, that's the trick, you see? So it's something tricky here. This comes from one somehow with a bit more algebra. So it's the affine lift of the complex projective space, but our affine setting is the real free one. Okay, so this is quite fun. Then also you can work out a bit, this model is actually faithful. So I have a matrix model like this, obtained by these matrices. Once again, this follows with a bit more algebra. And finally, similar results hold actually for all the subspaces of the real sphere, which are actually non-classical. So this is a bit more technical, but some of the idea is the same, projective lifts, things like that. So all this is Bichon, actually, all these things. And now the same things, of course, will work. Well, let's take a look at this. If it works for the subspaces, it will work also for these quantum groups, right? And Tora and everything, because everything lives in the sphere. So everything works also for these guys, and you have some complex analogs as well. So this is once again basically Bichon and Bichon du Bois-Viollet especially. So the first, there are many results here. Actually, I'm involved with some of them, but yeah, the story is that Bichon du Bois-Viollet did it for ON star, following some work of Maynard, Kuran, and Speicher. I think this idea of the 2x2 model comes from me and Karan Speicher, some probabilistic things. And before that, it was me and Roland Vernieu. We looked at ON star. Yeah, long story. And, so anyway, yeah, in this kind of results, not really, this kind of things, affine lift model. So that it was Bichon du Bois-Viollet here for ON star. And then Bichon for all these things, and then with me in the complex case too. Okay. So we have tools, we have quadruplets, so definitely we can check the axioms with all these tools. And let's go back. I mean, this is extremely powerful. It's this half classical business finally is the usual complex one, a bit twisted somehow with these matrices. So yeah, we're into classical geometry somehow. So everything can be done. We can check the axioms and we get our intermediate things too. Now the problem is that, well, is this anecdotal or not? So we've seen that we have uniqueness here, at least for the spheres appearing from these mirroring relations. Now it's possible to prove something, and this is the main result which motivates everything, that ON star is the unique equilibrium group between ON and ON plus. So that's me and Vernieu. It's well, you just look at the categories of pairing to classify them, and it's one-page computation. There's a unique solution there between non-crossing and all of them. So that's somehow it's unique. Okay, now let's go in the other sense. So yeah, we would like to complete now with hybrid things between real and complex. And so here the quadruplets, yeah, we are into classical geometry, right? Everything is known. We have to choose among these 4 problems which we'd like to solve. So the problem is that there are many solutions, I mean, for all this. So just discuss the standard solution. It's going to be a bit different from what we did with half classical. So there we had this result at the end, which is really, I mean, it's the unique easy thing. It's important. But here, even if you look at easy solutions, there are many of them. So just discuss the standard one. And the standard is simply obtained by taking the real thing and multiplying by a copy of T of the torus. So if you want more conceptually, this is the affine lift of the projective space inside the complex sphere. So that's somehow standard, and of course you can do it for everything, groups and tori. And well, this is classical thing, so satisfy the NCG axioms. That's not very complicated. And the remark is that these are not unique, so you can replace T by actually any cyclic group. They're generators. This is the R is infinity case, if you want, of this construction. So, but here not all the axioms are verified, so I'm not 100% sure that they satisfy NCG axioms. So somehow the idea is that we have this geometry, and this appears, I mean, it has some arithmetic versions, which are probably geometries too, but if you add whatever mild extractions, you get rid of all these guys, better forget about them. So it's finally, that's the solution. Now, so that was, yeah, getting back to the diagram, we have a point here on the bottom. We have to produce two more here and here. Well, it works too. Once again, multiply by T, but in the non-commutative setting, these are not really spaces, right? You cannot just multiply like that. So the idea is that the relations somehow corresponding to this multiplication by T are AB star is A star B. That's somehow define them. Now, in order to prove now the NCG axioms, you need some tools here. I mean, it's not that easy as in a classical case. And the tools is easiness. So these Horn groups are easy, and they come from the partition implementing these. The partition is simply two vertical strings, but colors are black, white, black, black, white. So it's yeah, this partition, you get easiness, and with easiness you can develop all the needed technology for checking the axioms. Technology being always, you need Weingarten, liberation results, and twist. Yeah, twist comes from easiness. We are sure while Weingarten also from easiness, and liberation. Well, it's also related to easiness. So you get all this. So as a conclusion, yeah, we've done the first part of what we wanted. We have this these geometries. No, the problem is are these unique or not? So here definitely on the vertical we have some uniqueness here in the real case, that's for sure. I mean, if we assume that our geometry is easy, definitely one star will be easy between O and O plus a unique solution. So that's a thing, but only in the real case. In a complex case, like if you look at these Monk-Weber papers, which are recent, there are many solutions here. So in a complex case, it's not going to be like this. Now, regarding hybrid geometries, here we've seen that there are these arithmetic versions, and actually these are the only solutions according to Tarago-Weber in the easy case. So once again, we have to assume easiness and some extra axioms, can get rid of them. And finally, what can we do in order to have uniqueness of all this? We have to get rid, so we need an extra mild extraction here on the bottom. We also need some extra axiom, like removing all this Monk-Weber stuff. And that extraction will be a bit more complicated. It will be something called orientation. I mean, the fact that the geometry must be recovered from its projection. Somehow it's in 2D, all this can be recovered from its real and classical version. It's going to be a bit technical. So let's get started. So in all this, yeah, every time we go back to easiness, so that's the thing to be developed, easy geometries. I mean, it's clear that all these things, the unitary inflection groups are easy in all these 9 cases. If you want also the tori spheres in some sense. So you have to understand what the easy geometry means. And well, the assumption is that the UK must be easy, right? And then there is a subtlety here. So remember that U appears as a soft liberation, if you want, of ON. So our axiom was U is ON T generated. That was part of the axioms. But here we have no T, right? It's not an easy quantum group, we only have K. So that's why we have to, well, U is generated by N and T. That was the hard thing. Implies the soft thing, which is U generated by ON and K. So now the problem is that the generation property for easy quantum groups is not known yet, that the class of easy quantum groups is stable by generation. So the problem is that if you take two easy quantum groups, it's not known that it's easy, this thing, so it's contained in the so-called easy envelope, that is the smallest easy thing contained in G and H. And also this easy thing, you don't really know that the category of partitions is the intersection of the categories of G and H. So that's why we have to introduce the so-called easy generation operation with braces like this, which means that this is the quantum group whose category of partitions is the intersection of the categories of G and H. So if you have three things and two inclusions, and both are conjectured to be isomorphisms, but we don't know. So now getting back here, we know that U is O and K with this kind of braces, but we have to assume something stronger than it's true like this. So that's well, a technical problem, but that's what we have. So easy geometry means that you get an easy and that the stronger version of the soft generation happens. Okay, now this, well, of course, easy, I remind you, easy quantum groups only depend on partitions, right? So we have two easy quantum groups U and K. So if we call D and D the corresponding categories of partitions, this must satisfy this and this. I mean, that's D is for the unitary thing, it must be pairings. E is for the reflection groups, must be partitions with even blocks. And what else can we say? Well, we have these two formulas, right? Connecting U and K. You can pass from U and K by taking this easy generation in one sense and by intersecting in the other sense. So at the level of categories, this the operation gets reversed. So generation corresponds to intersection and vice versa. So these are the two conditions on the categories. So again, easy geometry, you need partitions, pairings and partitions satisfying these, plus of course all the usual axioms. But these usual axioms, so yeah, something must be said here. I mean, what are STUK given DA, D and E? Well, it's very simple. So given D and E, I can construct U and K, right? That's the Tanaka duality. Now, if I have U and K, I definitely have S and T. I mean, in the axioms there are correspondences between S, T, U, K. So you take no matter which axiom giving you S in terms of U and K, no matter what other axiom giving you T in terms of U and K, and then you say that the other axioms must be satisfied. So all this, yeah, you have to think a bit, all this absolutely makes sense. Okay, so now that was definitions for the moment, but can we do the class? Well, not yet. So in connection with what I was saying, so UK appear like this, that's Tanakian duality. Now the torus and the sphere, as I was saying, you can take no matter which axiom and get your definition from there. For the torus, is very simple because this is just a diagonal torus of this beast here. So if you compute the diagonal torus, basically you have to impose this on U, but U with the off-diagonal things, zero by definition. So you get this group here, that's the dual of the torus. For the sphere, it's possible to try to formula, but it's a bit more complicated. It's tricky because the sphere, I remind you that it cannot be obtained from K itself. I mean, from K to S, we had to compose when doing our axioms. And from U to S, you have to take the first column space, and that the problem is somehow to plug in things which are only one column is complicated. So it's, yeah, but can be done at least in theory. So all this perfectly makes sense. The details being here for UK and T is just clear. So getting now into classification. So we have, well, in the real case, these are unique. Well, because what I was telling you, this result was very new that we have when star is unique, so it's over. In classical case, also we have unique under some mild axiom. That's because well, Tarago Weber, for instance, just have to kill these arithmetic versions of whatever extra axioms. Now, so we have two edges like this. We have uniqueness. The other two edges, I mean, the pure cases somehow. By pure, I mean either classical or free or real or complex. The other pure cases also can work it out somehow, the extra axioms. And in general, well, uniqueness, but you need definitely here to kill all this Weber stuff, right? And which is not exactly obvious. So actually, you need something combinatorially. You need something stronger than Weber because they just looked at U, so the unitary group. But you also need K here. So in terms of pairings, best is to start with pairings. The category of pairings, you see, you have this equation involving D only, because I remind you, let's go back to the previous slide. So see, we have D and E satisfying this and this, but if you assume that only D is known, one of the equations give you E, and the other equation gives you an equation on D. So that's your equation here, okay? This is E, okay? This must be E. So finally, you're looking into categories of pairings, satisfying this thing here. Weber looked in general at categories of pairings. They found many solutions. So with this in hand, well, you can cut a bit, and then finally, if you're ready to have uniqueness, you have to add little slicing, meaning that in this square you are in 2 dimensions and everything can be projected and reconstructed from the projections. So all this is a bit complicated, but anyway, that's the idea. I mean, under mild axioms, these are the only ones, the 9 ones. Now, more results. So let's go back now just to the spheres. Can we really improve this thing, the reflection permutation? And this can be improved. This is some very nice work I did with Mezarosh. So it's called monomial sphere appearing like this, but with any permutation, not only mirrorings. Okay. And in the real case, yeah, these are the 3 spheres. So the idea is that the permutations which appear, well, if you do a bit of combinatorics, it must be actually a subgroup of S infinity, which is an addition filter. Somehow there's a tensor operation on it. And you do some algebra to classify these things. So in the real case, we're done. Now, in the complex case, this is known yet. I mean, it would be very nice to have a result stating that the 9 spheres that we have are the only monomial ones. But this is something that we don't know. Okay, one more thing about classification, projective spaces. So if you look, so we've been talking, these projective spaces already appeared many times. So if you just compute them, here they are for the 9 geometries. You see they collapse only to 3 spaces. We have real here and here, then complex all over here, and free here, because you can prove this, that real and complex have the same projective space. So there's a very interesting thing here going on. I mean, instead of 9 geometries are fine. When we're passing to projective, we only have 3, real, complex, and free. So this is very nice. And once again, that's something that we did with the Mezarosh. We defined a monomial space, projective space, like something appear from this kind of relations. Well, you have to be a bit careful there. And, yeah, you have only 3 monomial projective spaces. This basically follows from the thing from the spheres. You just because you're into real case, so you see Pn minus 1 plus is at the same time real and complex. So for purposes here, of course, we'll think of it as being real. So finally, we need results for the real monomial spheres, and we had them. So we kind of export somehow that results. I was talking about here the projective setting, and get this. So it's very nice trichotomy, and this would actually suggest to look more seriously into projective geometry, non-commutative. So how to axiomatize these quadruplets? That's an interesting question. So you see, I find that was our idea. In projective, what are the arrows between this, all that, and these things are not very developed actually in the projective geometry. the free projective geometry. So very interesting question here. Okay, now in order to end now, we have some extensions for this. So first one, by twisting, the free things don't twist. That you can prove it, twisting at -1, but all the other things they twist. And the problem is that these don't fit exactly into the axioms. There are some problems with the QEs ones. And also the technology is not available yet. I mean, Weingarten is definitely available, and all this is known. I mean, the relation between spheres and unitary groups that's done. But the liberation things are not really known, and yeah, there are some ingredients missing. So modulo fix of the axioms and some ingredients still to be developed. Normally this should fit too. Now, one interesting question now, if you have, so I have our 9 diagram, and then another 9 diagram, which actually which coincides there on the free things, which don't twist, so now I have to intersect here, right? So up here you get 81 cases, and let's just look at the real case where you have only 3 times 3, okay? So intersecting the real things, this one here, and untwisted one here, I can put untwisted one here, so we have a 9 diagram. And the first problem is to, yeah, look at the spheres. These are not smooth actually, somehow are polygonal spheres, because, well, if you intersect twisted and untwisted, many things will collapse there. You get some kind of skeletons of spheres, things like this. So, but you can compute the quantum isometry groups, and it's quite nice. You get all these things which are all easy and very interesting. And Hn infinity is their own Weber thing, somehow the standard high liberation of Hn. So it's quite cool stuff. So maybe an intersection theory can be done too. But first is this one twisting. This is not done yet. This comes after. But some work on this is available on these polygonal spheres. No other extensions. There are many of them. So super easiness, all this business I did with Adam Skalski. Also there we have spheres, group, everything. So you just need to fine tune a bit the axioms in order to make them fit. Also like these Frelon things, partition quantum groups, other easiness things like done by Moritz and the others. And finally, I also have other types of noncommutative spheres. I mean, all these spheres like Kohn and Landi and the others by Alain, they well, they're subject to such things. Everything lives in the sphere, what we're doing here, okay? In the free complex sphere. So here too, I mean, when doing intersection twisting, they still live in a free complex sphere. When doing super easiness, they live in, well, you have to super modify it. But there are also the spheres more technical. So I think this philosophy in STUK can work in more gel settings. So it's far from being over. Yeah, so everything is very flexible. So as a conclusion, yeah, getting back now to Earth, yeah, that's at least one thing. I have these 9 main examples, some kind of classification results. I think these are the only ones for the extremely strong axioms. So in what follows in the next lectures, we'll develop these geometries. So that will be the idea to develop these geometries that we found, especially the free ones. So in the classical ones are known, and then the half classical are a bit well, very close to classical, also the hybrid ones. So we'll mostly focus on free geometry with 2 things: probability in mind, want to integrate there, see what we get, see if these things are a bit Riemannian for Laplacian, things like that. So analysis we have to do. And also, well, for the moment, we have only 4 objects, so we need many, many more manifolds, homogeneous spaces, and things like that. So these are just 2 things to be done: integration and homogeneous spaces. Okay, so see you soon for our next lecture.